All right, welcome to this explainer. Today, we're going to do something super cool. We're breaking down the absolute ultimate athletic action, a judo throw, and reverse engineering its core scientific blueprints. Whether you're a martial artist, a strength coach, or really just someone fascinated by human biomechanics, we are going to look at the exact physics, the kinematics, and the neuromuscular sparks that allow a human being to literally launch an opponent through the air with devastating efficiency.
So, what actually separates a merely good throw from a scientifically perfect one? It's incredibly easy to watch a massive dynamic movement like a judo throw and just assume it all comes down to brute strength or, raw aggression. But science tells a completely different story. A perfect throw is actually this beautiful orchestra of highly specific physiological adaptations, all happening in fractions of a second. And to truly understand how this works, we really have to look at the throw not as a single action, but as a sequence of distinct, interconnected mechanical steps.
To really get these mechanics, we've got to start with something called tsukuri. Basically, this is that absolutely crucial body-fitting moment where the athlete establishes a stable physical lever. Think of it as the ultimate setup phase. In judo, a technique generally breaks down into disbalancing the opponent, fitting your body in, and then executing the actual throw. Tsukuri is that critical middle phase. If this setup geometry is even slightly off, you just won't have the leverage to move a resisting human body, honestly, no matter how much you can bench press.
Section 1. The core engine. Building load-bearing armor.
You know the old saying, right? You can't fire a cannon from a canoe? Well, a perfect lever needs a completely ironclad base. Researchers actually test this active core stiffness using a really clever quick-release mechanism. In a fascinating study on torso stiffness, scientists preloaded athletes with a 16-kilogram mass using a cable system attached directly to their torso. Then, without the athlete knowing exactly when, an electromagnet instantly releases the weight. The researchers measure the gross stiffness and torso stabilization required to catch the body and stop it from violently jerking forward. This is active stiffness. It's your body's conscious ability to brace for impact or sudden force changes.
But then, to find your baseline passive stiffness, which is your natural armor when your muscles are totally relaxed, researchers came up with this crazy float setup. Athletes are placed on a cradle with precision ball bearings gliding over glass, allowing movement across 3 different planes of motion. The subjects were literally instructed to feel completely relaxed, almost like they were going to sleep, while electromyography verified their muscles were totally inactive. This allowed the scientists to measure the true baseline structural stiffness of the torso itself without any muscular interference whatsoever.
So how do we actually build this armor? Well, researchers compared 2 very distinct 6-week training methods designed to improve that vital core stiffness. They split subjects into 2 groups, one doing isometric training, which involves static, braced postures like planks and suitcase holds that minimize load on the spine. The other group performed dynamic training, featuring movement-based exercises like sit-ups and rotational medicine ball throws that place much higher shear and compressive loads on the back.
And the results are honestly fascinating. Active stiffness, that quick-release brace we just talked about, it remained completely unchanged across all groups, literally zero change. What this proves is that to safely build resilience, arrest painful vertebral micromovements, and enhance the ballistic limb movement required for a massive throw, you absolutely must train the core isometrically. 6 weeks of static bracing permanently upgraded the body's natural structural armor. It proved mathematically superior for enhancing passive core stiffness, while dynamic training produced a much smaller effect. A real game changer.
Moving on to Section 2, the biomechanical lever, mechanics of Tomoe Nagi.
All right, so with our core armor fully fortified and ready to handle massive forces, we need the exact spatial mechanics to actually launch someone. In a stunning discovery, sports scientists used rigorous kinematic analysis on elite intercollegiate judokas to find exactly what makes a sacrifice throw like the Tomoe Nage work. They tracked angles at the ankle, knee, hip, shoulder, and elbow. And out of all those moving parts, a single variable explains exactly 75% of the variation in the throw's success during that tsukuri phase. Just think about that. One joint angle dictates 3/4 of your success.
Through kinematic mapping, tracking the athlete's exact body positioning in real-world combat, scientists can mathematically track the joints during the tsukure phase. And that absolutely vital variable that controls 75% of the performance, it's the right knee joint. The angle of the athlete's right knee as they drop their center of gravity essentially operates as the master fulcrum for the entire technique. It's literally the engine for the whole shebang. The data here is crystal clear. Precisely angling that right knee at exactly 113 degrees, give or take 1.78 degrees, optimizes this physical lever for maximum throw efficiency. If the knee is bent even slightly too much or too little, the center of gravity shifts, the lever breaks down, and the throw completely fails. This highly specific angle predicts the efficient transfer of force and speed. Plus, researchers noted that this optimal positioning is intricately tied to the speed of muscle fiber contraction and peak knee flexion velocity. It is just a perfect marriage of geometry and physiology.
Which brings us to Section 3, the neuromuscular spark, power and altitude adaptations.
Now here's the catch. A perfectly angled knee and a stiff, isometrically trained core, they're absolutely useless without an engine. We measure this explosive power through a metric called the rate of torque development, or RTD. This is essentially the neuromuscular spark of the elite athlete. In sports, absolute maximum strength doesn't always win. What wins is the ability to access your maximum strength in a fraction of a second. RTD is basically the speed at which your nervous system tells your muscles, hey, fire with everything you've got.
So, to see if athletes could actually amplify this explosive spark, researchers tested a classic sports assumption. Does training at altitude actually make you faster? They took 19 elite male athletes and split them up. One group did 3 weeks of power-oriented strength training way up at a terrestrial altitude of 2,320 meters, while the other group did the exact same training right at sea level.
And the data they found is entirely unexpected. You'd naturally assume the altitude group would see massive gains, right? But actually, altitude training had a significant negative effect on the rate of torque development. The sea level group saw a positive increase in their explosive speed, while the altitude group actually got slower. Their muscle contraction time increased by 8.1%. The researchers concluded that the sheer stress of the altitude induced greater peripheral fatigue. Essentially, the lack of oxygen altered the muscle twitch, completely blunting the exact neuromuscular spark required for a lightning-fast throw.
All right, let's pull it all together in Section 4, the complete athletic equation, reconstructing peak performance.
So, piecing together the ultimate throw really requires harmonizing all these very distinct physiological, kinematic, and environmental adaptations. We've now successfully reconstructed the scientifically perfect athlete through 3 key pillars. Step 1. We stiffen the torso for maximum force transfer by ditching those endless crunches and replacing them with long-term isometric core training. Step 2. We use kinematic analysis to optimize our physical lever, locking in that exact 113-degree right knee angle to perfectly manipulate the opponent's center of mass. And step 3. We maximize explosive muscle twitches by prioritizing power training at sea level, completely avoiding the hidden peripheral fatigue traps of altitude camps.
As this research highlights, breaking down a chaotic, complex fight into straightforward, interconnected steps really takes the guesswork out of training. You're no longer just hoping to get faster or stronger. You're systematically targeting the exact mechanical points of failure and upgrading them. It's like solving a giant puzzle, piece by precise piece.
As we wrap up this explainer today, I want to leave you with a final thought to really challenge how you approach your own athletic training methods. Knowing what we know now, are you training your core dynamically when it actually needs isometric stiffness? Are your joint angles mathematically optimized, or are they just a habit? And is your environment truly helping your explosive power, or is it quietly causing fatigue? Dive into the science, refine your steps, and I'll see you in the next explainer.